Hey everyone, in this video we're going to continue our study of hypothesis testing. In this section we're going to cover hypothesis testing for a population mean using p-value. So finding the p-value is how we decide whether to reject a null hypothesis or fail to reject a null hypothesis. And just to remind ourselves, p-value is the maximum probability of making a type 1 error. And so we compare that probability to our significance level. So alpha is the significance level given. So like when we sometimes give, like in this first example, 0.05, so that's 5%. So that means that we want the probability, the maximum error, to have a probability of 5%. So very small. And then for this one, alpha 0.01, so 1%. We want the maximum allowed probability of making a type 1 error to be 1%. So that's kind of that's what our alpha is, and the p-value is that probability. So when our probability is less than the significance level, that maximum allowed probability, then we reject the null. So let's review these examples. The p-value for hypothesis test is 0.0237. What is your decision if the level significant is 0.05? So essentially we need to compare the p-value to the level of significance. So 0.0237 versus 0.05, which one is smaller? And here notice that our p-value is smaller than alpha. So then what will be our decision? Because our p-value is smaller than alpha, then we reject the null hypothesis, right? Our p-value of 0.0237 is less than 0.05. So we reject the null. And you can go by decimal places, right? The 10th place are the same, and then the 100th place, that's a 2 and that's a 5, so this is smaller. Now what about for B? 0.01, we fail to reject the null hypothesis because now our p-value 0.0237 is larger than 0.01. When we fail to reject the null hypothesis, another way to say this is that the alternative is plausible. Sorry, not the alternative. The null is plausible, right? When we reject the null hypothesis, that's when we can say the alternative is plausible. So it could happen. There's a high evidence that the null hypothesis, when you reject the null, that means the null is not true. You have enough evidence to say that you can reject whatever the null hypothesis is, which likely means the alternative can happen. When you fail to reject the null, that means that the null is plausible. And just to recap some of what we did also in the last sections is how do you choose your test statistic? So these are the different things that we can approximate or test. So population proportion if we have categorical data, mean if we have quantitative data, and then our standard deviation. And so in this section we're going to be focusing on the mean. So how do we know if I use the t-distribution versus the normal distribution? And just as we did with confidence intervals, that has to do with whether we don't know the population standard deviation or if we do know the population standard deviation. So when we know it, we use the z-scores, and when we don't know our population standard deviation, then we use the t-scores. And then after determining the hypothesis test standardized statistic, you find the p-value, and we identify what type of test you have. If it's a left tail test, then the p-value is the area in the left tail. For a right tail test, your p-value is the area in the right tail, which the area in the right tail is really 1 minus the area in the left tail. So let me write that. And this is because remember that our z-scores and t-scores give us the area on the left automatically. When you look at those tables, let me see if I have one handy. Yeah. The area that we get is the area that is on the left. Notice that the left tail is shaded. So that's why we use for when we want the area on the right, we say 1 minus the area on the left. And then for a two-tail test, the p-value is twice the area in the tail of the standardized statistic. And that's because you're looking at essentially the left tail and the right tail together. So you look up the z-score table or the t-score is going to give us the area in the left tail, but for a two-tail test then you have to multiply by 2 to get both tails. So let's try this example. Find a p-value for a left-tailed hypothesis test with a test statistic of z equals negative 2.223. Decide whether to reject the null hypothesis when the level of significance is 0.01. So first we need to look up the p-value for negative 2.23. So we go to our z-scores table, and you can access these via your textbook, or also I put them in the modules under statistical analysis tools. They're loaded in there. So negative 2.2, so here's negative 2.2, and then we want 3, so that's 1, 2, 3, the fourth one over. So negative 2.23 will be 0.0129. So that's our p-value. We want a left tail, so this is already given us the left tail area p-value. So that's what we want. So negative 2.23 is our p-value is 0.0129. So then with that p-value, what is our decision? So that means we need to compare our p-value to our alpha. So 0.01 and 0.0129, which one is smaller? And in this case, our alpha is smaller. So what's the outcome of our decision? And we can look back at the top here. If our p is greater than alpha, then we fail to reject the null. So we fail to reject the null hypothesis in this case. Now let's go to the next example. Find the p-value for a two-tailed hypothesis test with a test statistic of z equals 2.14. Decide whether to reject at the significance level of 0.05. So now we're going to look up 2.14 in our table. Now this is a positive z-score. So let's go to the positive z-score table. And we're going to look for 2.14, which is where? So there's 2.1, 0, 1, 2, 3, 4. So 0.9838. Now remember though, this is giving you the area to the left. So the nice thing about the bell curve is that it's nice and symmetric, right? So instead of having to do 1 minus the area on the left, let's look at the negative z-scores. And let's look at negative 2.14, because that will give us the same. That was already give us the 1 minus area. So negative 2.14, which is right there, 0.0162. So this is going to be our p-value, sorry, right here. And then we will multiply that by 2, right? So that's giving me this, and the two-tail will be, imagine that I can put another line here and shade the right area to that. So z is negative 2.14 here, and then it will be positive 2.14 here. And so the two-tail is the area on both. Actually, let me bring in my notebook. So essentially this z is what I'm calling negative 2.14, and the reason that I'm looking up the negative is because the bell curve is nice and symmetric, so this will be 2.14. Now the area here is the same as the area here, so those are the same. So looking up 2.14, to find this area I will have to do 1 minus the probability that z is less than 2.14. Oops, sorry, my handwriting somehow is not good today on the tablet. And right, but I want a two-tailed test, so I want both of them. So I can just look up already this probability. And so what I got for that by looking at our table, it was that it was 0.0162. So for a two-tailed test, I do 2 times that value, 0.0162, and when we do that with our calculator, or I guess we can just do it by hand, 2 times 2 is 4, and go on, so I get 0.0324. So this will be our two-tailed test. So let's go back to our notes. So we have our p-value is 0.0324. So now what do? decide whether to reject the null hypothesis at the 0.05 level. So compare 0.0324 to 0.05, and we can see that our p-value is now smaller, right? Looking at the 100th place, this is 5 and that's 3, so our p-value is smaller. So what do? We reject the null hypothesis, which then means that the alternative is plausible. So we have significance evidence to reject the null and to conclude that whatever the alternative hypothesis might be, it is plausible. So this is that was just review from the last couple of sections. New, now using p-values for a z-test for mean. So with sigma known. Remember, sigma is the population standard deviation, and this is a very rare case. We don't usually know our population standard deviation. So first, this is kind of the steps to do a hypothesis test for the mean. Verify that you in fact know sigma. Really, the first step is, do you know sigma or do you not know the standard deviation for the population? And then based on that, you're going to decide which test to use, which table, z-scores or t-scores. And then also verify that the population is either normally distributed or that the sample is greater than 30. Then state, based on the problem you're given, state the claim, write your hypothesis, null and alternative. It's a good idea to write it in words as well, so that you know then how to interpret the result in the context of the problem. Then specify the level of significance. This will always be given to you unless you're writing your own study. And then find a standardized statistic. So when we know sigma, we use z-scores. When we don't know sigma, you use the t-scores. Find the area that corresponds to your z and determining whether it's in the left tail, right tail, or a two tail. And this, the way you know whether you have left tail, right tail, or two tail comes from the alternative hypotheses. So we'll go over that in this example. Then make a decision based on your p-value compared to the level of significance, your alpha, and then interpret the decision in the context of the problem. So our first example here, in 2020, consumers in the United States spent an average of $90 on festive Halloween items. I think that with inflation, higher prices, the average spending in 2022 will be more than $90. So I randomly asked 40 US homes how much they had spent this Halloween. The mean was $102. From past studies, the population standard deviation is known to be $4 and the population is normally distributed. Is there enough evidence to support my claim at the 0.01 level of significance? And let's use a p-value. Now, oftentimes, like I said, sigma won't be known, but in this case, it is. So we have a population standard deviation is known to be $4. And notice that this is from past studies. So essentially this, if the standard deviation continues to be about the same, so like what is this? This data is from 2020. So like maybe in 2019 and 2018, the standard deviation was around about the same, around $4, maybe $3.75, maybe $4.25, but it's right around $4. So then we can say from past studies, the population standard deviation is known to be $4. So we can assume that for 2022. The population is normally distributed, so that already fits the first criteria. So it's normally distributed. And so let's state the claim. Let's write our hypotheses for this example. So what is the alternative and what is the null hypothesis? And oftentimes you'll be able to recognize one, and from that one you can write the other, because the other one is the complement. So the alternative and the null are complements of each other. So let's see. In 2020, consumers in the United States spent an average of $90. So this is given to me. So the average was $90. And it says is, right? Not more than or less than. Whoops, that's not what I wanted to do. Hang on. I just wanted to highlight it, not change the text color. So that means the mean is equal to 90. And my claim is that I think it's going to be more than 90. Right? My claim is that the average spending will be more than 90. So that those two already are my alternative and my null hypothesis. Which one is which? And now remember, the null hypothesis has to have the equals symbol, and the alternative has the other, the inequality symbol. So let's write them out. So for the null hypothesis, we're going to have, in words, we can say the average spending is 90. And in symbols, we can say that the average, right? So that's mu. So mu is equal to 90. So that's our null hypothesis. And then the alternative hypothesis is my claim that the average spending is more than 90. So in words, we can say the same thing. The average spending is more than 90. And so in symbols, this means that our alternative hypothesis, the hypothesis H sub A, will be the mean, so mu. Remember, the hypotheses, the null and alternative, are always written about the population parameter. So in this case, mu, the mean. And in the prior section, it was P, not P hat, right? So then here we're going to have the mean mu is greater than 90. And now this is when we get to also decide what kind of test we have. The alternative hypothesis tells you what kind of test. So because this is greater than, that means that this is going to be a right tail test. So that means you're looking at, when you have your C-scores or T-scores, we're going to be looking at the area to the right. Right, so that this is going to be 1 minus the probability of Z less than whatever our Z-score is. Because on our chart, we're always given the area to the left. So we have to do that. All right, so that's our alternative in our null hypotheses. So then what's the next step? So going back to the steps over here, we verified that sigma is known. We know that it's normally distributed. We have the level of significance. We have written the null and alternative hypotheses. So the next thing is find the standardized statistic. So our test statistic is Z equals to X bar minus mu over the population standard deviation sigma divided by the square root of n. So let's do that. All right, so then to find the test statistic, we need to know our X bar, mu. Well, we know mu based on our hypotheses. We have said mu is 90. So what's X bar? So let's read the problem again. So our claim is that the mean is 90, the population mean. Now in the sample of 40 people, right, so 40 US homes, so that's the size of my sample, the mean was 102 with a standard deviation of 4. So when we find our test statistic, I need to know my sample data. So X bar is 102, N is 40, and sigma is 4. And from our hypotheses, we know that mu is 90. So then let's find our Z. So Z is going to be X bar, so 102 minus 90 minus mu over 4, right, sigma over the square root of 40. And so let's do that on our calculator, and when we do that, we're going to get 18.97. And so notice that this, even back when we were doing things using the empirical rule, seeing how many standard deviations away from the mean we are, remember that a value was unusually high if we were more than 2 standard deviations away from the mean based on Z-score. So if Z is 2 or more, we were significantly high, right? Or significantly unlikely. So this is 18.97. That's super high. So now that we have our test statistic, let's find the p-value. And the p-value for a right-tailed test. Again, I know that from the alternative hypotheses. So we need to look up on our table Z equals to 18.97, which that's pretty high. So let's look up the p-value. And because this is a right tail test, we want, what do we want? We want the probability that Z is greater than 18.97. But our table gives us always the things to the left, so this is 1 minus the probability that Z is less than 18.97. So let's go to our t-table and find that out. So we're going to go to the positive z-scores and let's find our z 18.97. So notice that here it says 3.5, so that's the highest it goes, and up 0.999, so pretty much 1. So that is going to be, because ours is 18.97, that class qualifies for the N up. So it's 3.50 and up, so 18.97 will be here, so 0.9999. So that's what's going to be our p-value. So that means here we're going to have 1 minus 0.999, which gives us 0.0001. Now, what was our level of significance? We were told at the 0.01 level of significance. So we want to compare your p-value versus your alpha. So p-value versus alpha. So our p-value is 0.0001 and our alpha is 0.01. So what's the relationship? Yeah, our alpha or p-value is less than. So what happens when we have less than? We reject the null hypothesis. We can just say reject h sub 0. So rejecting the null, so let's go back and look at our hypotheses. So we reject the claim or the notion that the average spending for Halloween is $90. So because we reject the null, that means that the alternative is plausible. So it is likely that people in 2022 are paying more than $90 on Halloween spending. And I used social media to ask my friends, and I specifically ask friends in different states, and I asked them to ask their friends. And so it was a pretty simple random sample, right? Considering that I asked people in different states and they asked their friends. So it's slightly convenient because I ask people that I know, but then I don't know the people that they ask. So it makes it a little more simple. So the average was 102, so it makes it so that it is plausible that people are spending more than $90. And so what I asked was, what are you spending on candy, decorations, and costume for, say, a child? And so trying to keep it somewhat small, not in terms of all costumes and other things. I kept it to candy and decorations for this year. So here, because our p-value was less than alpha, we reject the null. So rejecting the null means the alternative is plausible. So let me say h sub a is plausible. So that means in the context of the problem, we can say it is likely that people are spending more than, or U.S. households, people are spending more than $90 on Halloween in 2022. So that is how you would go through doing a hypothesis test. So let's try, what about when sigma is known or not known? So when we don't know our population standard deviation, then what do we do? So when sigma is not known, this is the most usual case. It's very rare that you have the population information. Usually we use confidence intervals to try to narrow it down. So we may use a confidence interval to try to see where the population standard deviation is, and then we could then maybe using that population standard deviation use a z-score. But when we don't know it, we're just going to use a t-score. So the steps are the same. So make sure that you have a simple random sample, either from a population that's normally distributed or your sample is more than 30. State the claim mathematically, so write your hypotheses. And then specify your level of significance. This is usually going to be given, so this should really be step 2, and then three state the null and alternate hypotheses. But because we don't know sigma, we're going to use our standardized statistic. Is going to be the t distribution, so that should be the t scores, not t statistic, t scores. And we're going to use the degrees of freedom corresponding to the size of the sample. Remember, the degrees of freedom are n minus 1. Whatever the size of the sample is, minus 1. Then you find the p-value. And again, based on the alternative, then you know whether you have area in the left tail. So this means the alternative has a less than. Area in the right tail, this means the alternative hypothesis has a greater than. Area, a two-tail test means that your alternative hypothesis will have a not equals. And then your decision on what to do. Do you reject the null or fail to reject? So let's try this example. So a group of students estimated the length of 1 minute without reference to a watch or a clock, and the times in seconds were listed below. Use a 0.5 level of significance, so you can notice that significance is given, to test the claim that students are reasonably good at estimating 1 minute. These times are from a population with the mean equal to 60 seconds, and I should have said that it is normally distributed. So let me add that in. Okay, because we gotta have that is normally distributed or that your sample is larger than 30, and noticing this is not going to be more than 30 in the sample. This data can be found in StatCrunch in your group for this class, name minute estimation data set. Now the thing here that we're going to need is, because we don't know the population standard deviation, notice we don't know anything about the population, then we're going to need to find our standardized statistic. So let's find what that is. So let me copy that and take it to our notebook. All right, so now that we have we need to find our t statistic. So we need x bar and we need the mean. Actually, we do know stuff about the population. It does say that these times are from a population that is normally distributed with the mean equal to 60. So let's write our null and alternative hypotheses. So a group of students estimated the length of 1 minute without reference to a watch or a clock, and the times are listed below. Use a 0.05 significance level to test the claim that students are reasonably good at estimating 1 minute. So that means they're either do get it within to be 60 seconds or they don't, right? So then our null hypothesis will be that mu is equal to 60, and our alternative will be that mu is not equal to 60. Notice that nowhere in here does it say greater than or less than. So then this is going to be a not equals, which means this is what kind of test? Left, right, or two-tailed. This will be a two-tailed test. And so that's going to help us when we're looking for the p-value. So let's go to StatCrunch and look at the data. So what we're going to do is we click on StatCrunch from your My Lab, and then go to My Groups. And from your groups, go to our ARC Stat 300, and it was minute estimation. So there it is. So click on that. And so here is our data. So in order to find our t statistic, let's look at the formula for our t statistic. Notice that we need x bar, and we need the standard deviation, and we need the size of the sample. So back in StatCrunch, let's find the size of the sample. Let's do our summary stats. So go to Stat, Summary Stats, Columns, and then select our column, the 1 minute estimation, and then we're going to select the mean, then control standard deviation and control n, and compute. And there is our data. So the mean is 63.2, standard deviation is 18, and n is 15. So let me copy that and take it to our notebook. All right, so now that we have this, we can say to find our t statistic, I can say then t is equal to x bar, which is this, and then this is our s, and that's our n. So 63.2 minus the mean, which is 60, over s, 18.03, over the square root of n, so the square root of 15. And then this will be our t, so what do we get? Which I get 0.68. And so now if we go to look up for our p-value, so to find the p-value, we need the degrees of freedom, which is going to be 15 minus 1, which is 14, and our 0.68. So when we go to our t-distribution table, which is not that one, it's this one. Notice that there is no 0.68 in anywhere in here, right? Our areas don't include that. Like the smallest one we have is 1.282. So then how do I do that? I can't do this. And so that's okay. So we're going to stay then with StatCrunch. So we found our t statistic, but unfortunately the table doesn't help us. So now what we're going to do in StatCrunch is find the hypotheses. So we're going to go to stat, but instead of summary stats, we're going to go to t-stat, right? Because we have a t statistic, one sample with data. And so choose your column for the data. And now notice that here is asking us, what do we want to do? Do we want a hypothesis or do we want a confidence interval? So we could have also done confidence intervals from the previous sections using StatCrunch, but here we're going to do a hypothesis. So this is going to be mu is 60. So look at your notes and you put in your hypothesis here. This is not equal, so that's okay because that is what our alternative hypothesis is a not equals. If we were doing the prior example, which was greater than, then I would have done the drop down menu and do greater than. So, but here we'll keep it at not equals. Our confidence or significance level was at 0.05. It is 0.05, but if it wasn't, like if you wanted to change it to 0.01, then just click on show critical value and then you can change it. But in this case, we'll just leave it at 0.05 and then compute. So click compute and it gives us notice that it gives us the t statistic, which is the same value that we found, the 0.68. But what I want you to focus on is the p-value. Our p-value is 0.5031. So the p-value is the probability of obtaining a result just like the one in our sample, right? So that's our p-value. So let's copy that. But this is kind of nice because notice our t statistic is 0.68, which is what we got, 0.68. So that means that the work that we were doing was correct. It's just that unfortunately we can't use the table. So our p-value is 0.531. So versus our alpha, which is 0.05. So what can we say? In this case, right, our p-value, so 0.5031 is greater than alpha. So what do? What is the result? When it's greater than, then we fail to reject the null hypothesis. And so what was the null hypothesis? The null hypothesis is that people are spending on average, oh wait, this is the other one. This is the one that is the minute. So the null hypothesis is that students are reasonably good at estimating 1 minute. And we said we failed to reject the null hypothesis. So that means that the null hypothesis is plausible. So it is plausible the students are reasonably good at estimating 1 minute based on this sample. So that's what you will say in the context of the problem. Now go ahead and try example 2 on your own. So this is the data that we use for the sleep study. So you can find it in StatCrunch again and do the same thing for this. You can look at the notes from section 7.2 and see what the null and alternative were. I copied them here for you, but do a use the confidence interval at the 0.05 level significance to make a decision about this claim. The claim was the students at ARC sleep on less than the recommended average, which of 8 hours of sleep. So try that on your own and see what you get. And you can do it in StatCrunch since the data is already there. So this will be good practice for StatCrunch. So I'll record a video and so that you can check your work for that. Okay? Email me if you have any questions.